This lecture will look at the problem of extracting useful features from data that may not be in the most convenient format for us to use, whether in supervised or unsupervised learning. So I'm going to talk a bit about the motivation for this, for extracting features. The actual techniques used will depend a lot on the particular problem that we're trying to solve and the kind of data we are using, but this will just be a generic overview. And then we're going to look at principal component analysis, which is a well-known statistical technique, just as an example of the kind of things that we can do with the data. Later on in the course, we're going to look at manifold learning, which gives us a better approach than principal component analysis for dimensionality reduction and reducing the amount of features. But then we're going to look at self-organizing maps, which are a form of unsupervised learning that can help us organize the data better. And we're going to look at an example looking at patterns of development in different countries to illustrate this problem of extracting the relevant features and then reducing dimensionality in a way that helps us visualize and understand the structure in the data. So let's start with the problem of feature extraction. In many cases, we have data that is not well structured in a table where we have specific features that we can use for machine learning, or that have lots and lots of different features that do not capture really what we want. So we want to transform that data into a more useful data set. This can be, for example, if you have images which are unstructured data or sound files, documents, and so on that do not really have a tabular form where you can say this feature has this value and so forth. So in those cases, you need to transform that raw data into something, a kind of a table that you can use for machine learning. In other cases, you may simply have too much information, too many features, and you want to summarize things, capture a subset that has the relevant information for you. So one very widely used solution for this, for trying to shrink down the number of dimensions that we have, is principal component analysis. And I'm going to talk briefly about this to give you a general idea of this approach. So in principal component analysis, what we want to do is to find an orthogonal set of vectors, so an orthogonal coordinate system that will lead us to fewer dimensions than we start with, but aligns the vectors with the directions in which our data has the greatest variance, so the greatest dispersion of the points. Basically, the first vector will be aligned with the direction where our points are more spread out, and then we will choose a second vector perpendicular to the first one that is aligned with the most remaining variance, the most remaining dispersion, and so forth and so forth. And we keep the first k vectors so that we reduce from our original dimension to k dimensions, the ones that we choose. So let's imagine that we have this data set in 3 dimensions. As you can see, the points are spread out along this diagonal here, mostly, so it's like a cylinder-shaped cloud here. But we have these 3 coordinates in our original data. What we would like to do is to reduce this to 2 dimensions, but without squeezing together the points too much. So if we project everything along this long axis, we can get the points more spread out than if, for example, we project everything like this, where the points become too overlapped. If we wanted to use this then for clustering or classification or something like that, in general, we may think that it's best to keep the points as much with as big a variance, as big a spread as possible. So this is the idea of principal component analysis. We start by computing this scatter matrix, which is basically the covariance matrix multiplied by a factor. And this involves first computing the central point of our cloud. So this is just the average of all the coordinates in our data. And then we're going to compute a matrix, a square matrix, this scatter matrix, that has as many rows as the number of dimensions in our original data. So in this case, it would have 3 rows and also 3 columns, the same number of columns. And this is obtained by taking, for each example in our data, the vector that goes from the center of the cloud to that particular example, and then using that vector as a column and multiplying by the vector as a row. And this will, when we do this matrix multiplication, we get a 3 by 3 matrix that we are going to keep adding to the scatter matrix. So the scatter matrix is the sum of all of these products for all the examples in our data. And now that we have this scatter matrix, this gives us an idea of how the cloud is spread out to different directions, because we are using this for all the vectors. Basically, the vector between each example that we have and the center of the cloud. So this scatter matrix represents the shape of the cloud of points. And now we're going to find the eigenvectors for this matrix. And an eigenvector is a vector that when you multiply some matrix by that particular vector, what you obtain is a vector with the same direction as the original one, just minus some scaling factor. So this will be the scaling factor lambda here is the eigenvalue, and this is the eigenvector. So basically these are the vectors in which, using the matrix as a transformation, we retain the same direction and we simply stretch or compress in that particular direction. So if we find the eigenvectors of the scatter matrix and we sort them by the eigenvalue, we can pick the first eigenvectors, which are the ones where the stretch is longest, so to speak. So basically where most of the variance, most of the dispersion of the points remains. This is easy to do with NumPy, because you can compute the mean point like this. If you have your data with the features, the coordinates in columns, and each element, each point in a row, when you compute the mean with an axis of 0, which is along the rows, you get a vector, in this case a vector with 3 coordinates that is the mean point of this cloud of points here. And now we can compute for each point the vector between the mean and that particular point. We reshaped it to a column vector, so that now we can compute the dot product of that column vector and the transpose of that vector that you can obtain with this capital T attribute here, which will be the same vector but as a row instead of a column. And this gives us this square matrix, which has as many rows and columns as the size of the vector, so the number of features that we have, and we keep adding it to the scatter matrix, which began at 0 with 3 by 3 in this case, and now we add this product for all the examples in the data. So this is the scatter matrix that we have at the end, and now we can compute the eigenvectors. The computation of the eigenvectors is outside the scope of this course, but we have this in NumPy in the linear algebra module. We have a function to compute the eigenvectors and the eigenvalues. So when you give it the scatter matrix, you will get a matrix with the eigenvectors, so all these vectors here, and an array with the eigenvalues. So now we can choose the largest ones. You can see it's the first eigenvector has the largest eigenvalue, and the third eigenvector has the second largest eigenvalue. And this corresponds, these 3 eigenvectors correspond to these 3 vectors here. So you see the first one was aligned with this diagonal where the points are more spread out, and then the second one with the direction where in a perpendicular direction where the spread is the greatest, and then the third one is perpendicular to the other two. So we can pick those that have correspond to the greatest variance by looking at the eigenvalues that you get here. And now we choose the two vectors, the first one, index 0, and the third one, index 2, to create a transformation matrix so that we rotate and project our data into 2 dimensions. We can do this with a simple algebra multiplication of this matrix and the transpose of our data matrix, but this basically is just those simple algebra operations to transform the coordinate system in a set of vectors, and then we can plot this in 2 dimensions. So basically what we are doing is we are going to rotate our data points so that they are aligned first with the vector that corresponds to the greatest dispersion, and then with the other axis with the other vector that corresponds to the largest remaining dispersion, and project everything in 2 dimensions. So we get this first coordinate here is along that diagonal where we have the greatest spread in our points, and the second coordinate is along the orthogonal vector that has the most remaining variance. So we get a projection from 3 dimensions to 2 dimensions that preserves as much as possible of the variance while being a linear transformation of the data. So we're just rotating and projecting. We are not distorting the data in any additional way with a nonlinear transformation, but we are doing this rotation and projection in a way that preserves the most variance. So with scikit-learn, you don't need to actually do all those steps to compute PCA. You can use just the PCA class here, and it works as usual. You have the fit, and in this case the transform method. You can also use a fit underscore transform, which does both things in one step. But basically what you do is you create a PCA object with the number of components that you want to retain, and then you fit it to your data, so it computes the eigenvectors and chooses those with the largest eigenvalues, and then you can transform any data set into a reduced dimension by rotating and projecting according to the best n components that you selected here. So in this case, it would be the 2 best eigenvectors will be used to rotate and project the data so that you could reduce from the original dimension into the dimension that you want. Okay, so let's look at another method now for reducing dimension here, and this is mostly self-organizing maps are mostly used for visualization of high dimensional data. And the idea here is that this is based on artificial neural networks. We can imagine that we have a set of neurons in that we are going to for which we are going to adjust the weights, and each neuron will receive as input the examples that we have in our data. So the input dimension for each neuron is equal to the dimension of the input space that we have. But we have these neurons connected in a 2-dimensional matrix. So each neuron has its own neighbors in this matrix, and you can imagine that we are spreading them out like a sheet of paper or something like that, where we have the neurons disposed in a regular 2-dimensional grid. So we can measure 2 distances here between the parameters of each neuron and the input vector that we are presenting to the self-organizing map, and this will allow us to compute this distance in the space of the input data. But then we also have the distances between neurons, because the neurons are spread out in this grid, and we know how far away in the grid each neuron is from the other. So the idea is that we're going to start with small random numbers for our neuron parameters, There are some ways of sampling this, but we can just give them random numbers close to zero. And then for each example that we present to the network, we're going to find the neuron that has the parameters values closest to the values of the features of the example we are presenting. And this will be the best matching unit. And now we're going to adjust the weights of this neuron, the one that is closest to our example, so that it becomes closer to the example. We're going to adjust it so the parameters of the neurons become closer to the values of the features of the examples. And we're going to do the same thing with a decreasing rate to the neurons that are close to that best matching unit in this two-dimensional matrix. So basically we're going to pull everything, all the neighbors, in the same direction. And we're going to do this and gradually decrease the learning rate, so gradually slow down the way the neurons move, and do this repeatedly with many epochs, so passing all our data set many times through the network until we reach a stable situation. We stop because we are decreasing the learning coefficient. So the idea is that we have our points here in this cloud. We start with our neurons at random, assigning each neuron a random set of values to its parameters. And when we present an example, we find the neuron that is closest to the example. So we look at the values of the parameters of the neuron and compare them with the values of the features on the example, and we find the neuron that is closest to the example. So now we're going to pull this neuron closer to the example, but the neurons that are neighbors to this one, and the closer ones the most, will also be pulled in the same direction a bit. Not as much as the closest neuron, but along the same line in the same direction by a smaller amount. And this propagates decreasingly along the network. So the network stretches in this direction. And we keep doing this many times until eventually our network will be like a piece of rubber stretched over the shape of our data. And although the shape of our data here is in n dimensions, it can be in a very high dimensional space, we still retain this topology of the two-dimensional organization of the grid. So now we can represent this in 2 dimensions if we go along the grid of the neurons. Let's do a simple example of going from 3 dimensions to 2 dimensions using colors. As you know, we can represent colors with the 3 channels, red, green, and blue. So basically, this would be black, 0 red, 0 green, 0 blue. If we put 0 red, 0 green, and 1 blue, we have blue. If we put 0.5 on all, we have gray, and if we increase a bit, we have light gray, and so forth. So I created here a list of colors and the names for the colors. And now we're going to organize things in this 3-dimensional space where these colors lie. We're going to project this into 2 dimensions. So we're going to look at a range of colors and project them in 2 dimensions. This is just an outline of this mini-SOM library that you can download from here if you want to experiment. So this is the mini-SOM class that you initialize by specifying the dimensions of the grid of the self-organizing map. So this would be width and height of this grid of neurons. X times y gives you the number of neurons that you have. This is the length of the input, so how many dimensions you have in the input, and this will allow you to parameterize the spread of this function that will pull the neighbors along with the best matching unit. So you can make this narrower, it only pulls the closest neighbors, or you can make it larger and pull farther away more. And also the learning rate that you start with, which then will decrease along the training. We initialize the weights of all these neurons, so these x times y neurons get initialized at random. And when we train, basically we are presenting the data, a number of repetitions of all the data, and this will, for each point in the data, choose the best matching unit, stretch the sum in that direction, and keep doing this for a number of epochs. So we can use this with our colors examples. We're going to initialize the weights of the neurons by giving first the actual data. So the initialization method here is picking coordinates for the neurons in the sum by picking randomly at examples in the data. So our data is just a large list of colors, and we're going now to train the sum using 10,000 iterations going through our list of colors. And this basically will spread this two-dimensional grid of the self-organizing map with this number of neurons that we decided here, which is 20 by 30 neurons. We are going to spread this grid of 20 by 30 neurons in a way that corresponds to the distribution of the colors in 3 dimensions. However, the grid of the sum is 2-dimensional, and we can represent that. So now we can create an image using the actual weights of the self-organizing map. So this is easy to do because we have 20 by 30 neurons, but each neuron has 3 weights which correspond to its position in the color space for red, green, and blue components. So we can actually use this sum as a color image and represent it, and it will be, it has this aspect here. So here you can see a projection from the 3-dimensional color space, where you have all these combinations of red, green, and blue, into 2 dimensions using the sum. And now you can see how the related colors tend to be closer together, for example, red, yellow, and so on. But the sum tries to organize this in a way that optimizes the correspondence between the neurons in the sum and the colors in the color space. So you can imagine that this is like a rubber surface that we stretch it and spread out to represent this distribution of colors. Here, the names, I just put the labels by selecting from the sum. So this winner function gives me the neuron that has the closest, that is most similar to the example that I present here. So if I go for the colors corresponding to these names that are defined here at first, I can pick the neuron that is closest to each of these colors and then create the text there in that position. So this allows me to label the red, pure red is here, yellow is here, lilac is here, and so on. Okay, so let's look at a more realistic example of using self-organizing maps and feature extraction. We're going to look at data from development in different countries here at this site, Gapminder. By the way, this site has lots of good visualization tools, so if you are interested in this kind of subjects, you can take a look at the site. It will be useful. But you can download indicators in Excel format with different indicators for the countries, and each file is organized with 1 row per country and 1 column per year. So we need to organize the data by country, and also we need to use several indicators to try to get the profile of development for the country. So for this particular example, I'm going to look at these 4 indicators: per capita gross domestic product, life expectancy, infant mortality, and employment rate for all people over 15 years old. And this is the kind of data that you have. So for each indicator, this is life expectancy. You have columns for the years, and you have rows for the countries, although there are missing values. So you don't have values for all the years for all the countries. And if you plot the different indicators, I normalized all of them, so between a range of 0 and 1, because they indicate different things. You can have GDP that goes to GDP per capita goes to thousands of dollars. Life expectancy is in years, so it's around decades. Employment rate, and so all of these are in different units. So we need to normalize them in order to get them in the same approximate scale. But once we do this, we can see the kind of data that we have. For example, for Portugal, we have information on life expectancy, some estimates here, then actual data for this time span, and then some predictions for the future. We have information on employment only for these years, gross domestic product for these years here, and childhood mortality for these years. So you see, we don't have the same information for all the years. And also when we compare different countries, the gaps are different. So you see, we are missing mortality data here on the United States. We have different time spans in different countries for those indicators with gaps and so on. So the problem here is, how can we use this data for machine learning, for training a SOM, for example, in visualization, or if you wanted to create some predictive models based on this, we first need to extract from here some useful features that represent these different patterns. So this will be the first step. We're going to start by extracting features, and one thing that we can do is we can take each of these data series, each of these time series, and represent it with a simple polynomial curve. So let's consider that we're going to adjust a third-degree polynomial to each of these lines that we have here. So if we do this, we have 4 indicators for the countries. A third-degree polynomial has 4 different parameters. So the one that multiplies x cubed, x squared, and x, plus the constant. And so in total, we can reduce this to 16 dimensions per country. And we would have these 16 features that are present in all countries, regardless of the gaps that we may have in the original data. Because now these features represent the shape of these curves. So this is an example. I draw here in gray the set of all countries, all the curves for all the countries, but this is the example for Portugal. We have here a curve representing the shape of the childhood mortality, another one representing the shape of lifespan, employment, and so on. So these curves, they don't adjust well outside the range where we have the data. For example, this curve adjusts well only here, which is where we have the data, and then it misses completely because we're outside the range of the data. But what we want from each curve is not actually the line itself. This is just a representation. What we want are the 4 parameters that we got when we adjusted the third-degree polynomial. So there are 4 parameters that represent this shape, 4 that represent this shape, and so on. And for different countries, we'll have a different set of 4 parameters representing the shape of the data that we have for life expectancy, GDP, employment, and such. And now we have all the countries represented in this 6-dimensional space with the 4 parameters per indicator and 4 indicators. To visualize this, it's hard to visualize data in 16 dimensions, so we're going to use self-organizing map to project this into lower dimensions, and then label some countries in the self-organizing map so that we see how they are distributed in this 2-dimensional space. So we can create a mini SOM. In this case, it's 30 by 45 neurons that I'm going to use. The number of features is 16. This is the number of features in our data. And we start with these parameters for learning rate and segment, and now we initialize the weights, and we train our data using the descriptors that we got for our country. So this matrix with the descriptors has 1 row for each country and has 16 columns which correspond to the 4 parameters of the curve adjusted to each of the 4 indicators. And now we're going to create a figure showing the distance map. This distance map tells us how stretched the self-organizing map is at each neuron, basically the average distance to the neighboring neurons, and we're going to represent this with this bone color map that is from black to white. And we're going to do the same thing as before. We're going to label some countries by picking the neuron of the self-organizing map that is closer to that country, and then drawing the text in that location of our image. And this is the result that we get here. So you can see these countries here: United States, Germany, Netherlands, Switzerland, Canada, Austria. These are United Kingdoms, Sweden, and so on. They are all bunched together at this part of the self-organizing map. Portugal is here. Then we get countries like Kazakhstan, Cuba, Russia, Albania, Syria over here, Madagascar, Brazil, so they are on this side. There is one strange country here, which is Qatar, and you can see this bright color indicates that the sum is very stretched in this region. So the distances between the neurons became very large, probably because Qatar, due to the sudden increase in richness in gross domestic product when it started selling oil. This is probably a very strange country compared to the others when you look at the development profile of life expectancy, GDP, employment, and so forth. So it probably has a very different profile from the other countries. So it stretches the self-organizing map and is here isolated at this side. But this gives us an idea now of how the countries relate in the pattern of development over the last 2 centuries or so, reducing from 16 dimensions to 2 so that we can visualize this. But the first step was obtaining those 16 features, in which we had to work with the data and somehow extract relevant information that we could put in an organized form in order to be able to pass on to these kinds of algorithms. Okay, so to sum up, we saw the motivation for feature extraction. We don't always have data with nice organized features. We can have things that have missing data or different time ranges or things like that, and we need to organize the data, extract features in some way. We saw PCA as one classical example of dimensionality reduction. Self-organizing maps is another way of reducing dimensionality. It's often used for visualization in 2 dimensions. But for feature extraction itself, we often have to think about specific solutions depending on the problem that we're trying to solve. And I gave this example of the countries just to give you an idea of how we can attack this kind of problem. So in this case, we have very messy data with lots of gaps, but we tried to capture what was interesting for us, which is the shape of the progress of those indicators by fitting to some curves, in this case polynomials, which have a fixed number of parameters. So we managed in this way to represent the overall shape of the development of each country with 16 parameters, 4 parameters for each of the 4 indicators, and then we used some to reduce from these 16 dimensions to 2 dimensions in order to visualize the organization of the countries. So if you want to read more about PCA with scikit-learn, there is in the documentation a brief explanation of PCA, and you can see more about self-organizing maps in Wikipedia, but this is a simple concept using these neurons to try to approximate the data in the original space, but keeping the neurons in some topology in 2 dimensions so that then we can represent everything in 2 dimensions.